Okay. So let's talk about that last question. Okay. And there's two different versions of how you can do this. I don't care which version that you do, but once you start that version, stick with it. So let me kind of get you started if you're going to do the variable thing. So the whole key to this is that you are making a comparison between, so here's your circuit, boom, got one here, got the switch up here, another bulb, okay, and then your battery here, okay? So the question being is that what happens before and what happens after? Now, conveniently, all of these resistors are the exactly same. Okay, they're the same voltage, but you treat them as resistors. So before the switch is closed, okay, before the switch is closed, you've got these two bulbs in series. So how would you calculate that total resistance?
Just add
them together because they're in series, right? Yeah. So you can lay this out and go, okay, and you want to keep this organized. Do not just write down random things and think, I'm going to know what you're talking about. Okay? You want to lay this out, though, basically like a two-column proof. You're going, here's what's happening before you close the switch. Here's what's happening after you close the switch. Okay? Writing down random things is not a proof.
P1 and P new, is that good?
Huh?
P1 and P new.
I can do that.
Okay.
I just have P close, P
What's up?
open. He's not looking.
Okay.
I don't know who he's looking at.
So, before you close it, if you're doing the variables, you can sit here and go, okay, well, that's R1 plus R2, but these are the same, so that becomes 2R, right? Now, if you var it up, okay, I'm just saying, if you var it up, then the current would be equal to what? V over 2R. Okay? Makes sense, right? So if you want to then look at it in terms of power, and power equaling I squared R, because the whole key to this is that you're focusing on what's going to happen to the brightness of bulb 1. So that power, if you went with this method, you go, okay, well that's V over 2R squared times R, right? See where we're going with this. So that becomes V squared over times R. So that's going to cancel out. So you could, I'm just saying as an option, you could write this as 1/4 V squared over R is going to equal power. Okay? But that's okay. It's a fraction. It might
Is it cool if I use the voltage one instead, like the voltage resistance one? Does that show?
as long as I can track what you have done. Okay? If I can't track it, then I don't care how you did it. It's not going to make any difference. Now, once you close the switch, okay? Once you close the switch, what happens to the resistance in that part of the circuit? Why?
Parallel path. The way you
Parallel path, right? So then you can go, okay, this is after I close the switch. So that's going to be 1 over R plus 1 over R plus R, right? Cool with this. So if you do this math, you get out of this then, so that's going to be 1 over R, 1 over R, and all that. You get, track that, 3/2 R.
Good. Wow.
So the initial total resistance was 2R. The new resistance is 1.5 R. So this is the whole point of parallel circuits. By putting them in parallel, what happens to the entire resistance in the circuit? It goes down. Okay? Which is, again, Easter is coming up. Your siblings are coming home and your mom cooks in parallel. Great. Resistance in the household is going to go down because your mom cooks in parallel and everybody gets the same amount of food. Now, if you repeat the process, this is where you have to stay true to the process. If you're going to ver it up, then you're going to do the same thing. Then your current is going to be V over 3/2 R. Okay? You're going to follow the same process. Whatever you do with one, you're going to follow that same logical thought process into the next step. Then if you come in here and go, okay, well that power now is going to be V over 3/2 R squared times R. Okay? See where we're going with this. So then that becomes V squared over 9/4 R squared times R. We lose one of those. And then you flip this up, and then you get 4/9 V squared over R is going to equal your power. Now you can make a comparison. So the first one was 1/4 V squared over R. The second one is 4/9 V squared over R. Okay? So now the only thing you're left comparison, on a comparison basis, is what's bigger, 1/4 or 4/9. 4/9 is bigger. So you have just proved that once you close that switch, the power is going to be bigger. Okay? Now, if you don't like that, you go, man, I hate working with variables. Great. You're going to repeat the same process. The only difference is instead of R's, you're going to put in 10 ohms. Instead of V, you're going to put 20 volts. Okay? But it's the exact same fundamental process. You have to be able to say, here's the power. This is what I'm going to look for. Here's the power before you close the switch. Where's the power after you close the switch? Okay? And mathematically, your power afterwards should be bigger than the power before you close the switch. Okay? That's the whole point of the exercise. Now, when you get to that last part, on part 3, okay, how does the result of your derivation of part A relate to your explanation of part A1? Okay? So, how do you make that comparison? Okay? You can just say, hey, 4/9 V squared over R is bigger than 1/4 V squared over R. So, not necessarily. Now, the tricky part is actually when you get to part 2 on A, where it says, derive an expression for the power P nu expended by bulb 1 after the switch is closed in terms of P1. So let me give you a simple example. Let's say that you get a new boss that comes in. And your new boss looks at your hourly wages and goes, man, we're going to bump you up to $20 per hour. Okay? Like that, boss. Okay? Because your old boss had you working at $10 an hour. So how could you express the new boss salary in terms of the old boss salary?
2 old bosses.
Yeah. So the new boss's salary is 2 times the old boss salary. Now, how'd you get that?
20 over 10.
You took the bigger value and you divided it by the smaller value. Okay? That's what you did. So you need to do the same thing here. You need to take that new power, if you work with these variables. So you're going to take 4/9 V squared over R and divide that by 1/4 V squared over R. Now, if that you don't like that, if you don't like dividing by that 1/4, what could you do?
Multiply by 0.25.
Multiply by 4. And then you get 16/9. So then you would say the new power is 16/9 greater than the old power was. So it's the same thought process, you write that out. Okay. Are we cool with that one? So, most important thing that you have to do on a problem like that is to be able to articulate and lay out a thought process, not that you can follow, but that I can follow. Okay? So, anyway, are we good? What? No, you can't have the light back.
I was gonna.
Okay, good.
Could I ask about cluster 9 and 11? Like why they?
Why they do the voodoo they do?
Yeah, I think I got into a test and we confused. Why are some of them turned off? What's going on?
No, I have one.
Shut up.
Yo.
Think about it. Both those they combine.
Oh, okay. So 20 over 40.
Take a picture of this because I want to
That's what I have.
circle so you can out there.
See, I even got the prediction.
I don't know where I got this one.
I only got one.
I swear he's gonna put all of these
Okay.
tests and be like,
So, the whole key to this on number 9
yeah.
is understanding the direction of the battery feed. Okay? So both of these have the positive terminals up here at the top. And again, we're going with old school Ben Franklin. Thank you very much for positive charge. Okay? So if you look at this, so this is sending this current in this direction. This one's sending the current in this direction. Now, they're going to run into each other. Okay? Now, if you don't have that middle section,
No bueno. Nothing.
nothing. Okay? But because of the fact that you have given it an outlet, then it's going to take that path. But not only are you taking that path, you're merging two currents together. So what's going to happen to the current flowing through that one?
Bigger. So why did they skip over the top two? Because weren't the top two supposed to be off?
No.
What?
No.
Oh no! On cluster 9?
Wait, what do you
No.
Brad, what'd you get? It was all for you.
But
That was my prediction.
there's no way they can skip nothing. No.
So for me on number 9, my prediction was
Mine were off.
the middle
Alright?
one said it was the top two
I
were
did
two.
everything
Yeah.
one.
But when you just verified that, I said like,
Wait, so
oh,
are these like
current
low?
doubles because like they are fine. But when I ran the thing, all of them were the same.
This
is what I was thinking.
Okay, what about 11?
This one was higher.
The chairs is low.
Yeah, the middle one was higher. The middle one was
It
higher.
shouldn't have been.
Yeah, the middle
Come
one.
on,
The
Mike.
top two were the
If
lowest.
you actually built that, I promise you the middle one was right.
Okay, maybe.
Okay, that makes sense.
Yeah.
Why would the middle one be?
What about
My
11
prediction
though?
was
Hold
right.
on,
No,
just
no, no.
chill out.
We got that time.
This is
the original.
Hey, whenever the capacitor is charged, it just acts like a series when the capacitor is fully charged.
Become one, and then when it's fully charged, it acts like it's outside one.
P1
Yeah,
was
yeah. So
143.
it would just feel like a normal series circuit. Yeah, okay, that's what I'm asking.
P1 was 143.
Hey, Big Mike, what you got on left?
I don't know, but it's one. The actual is 1, 2, 1.
That's
middle
how-
one's 2.
1, 2, 1. That's what I got.
11?
On cluster
Yeah.
11?
Yeah, that's the
Yeah.
one. 1, 2, 1.
No, it's one off one.
I got that.
Two's off.
Yeah, how do you calculate resistance?
It's off, but you got to wait.
Guys,
No, we said that off. It's off.
Yeah, so it's less bright.
It's not
Yes.
quite.
Oh, I might have got it off. I just heard.
I knew I'm making a
Are
ratio.
we supposed to right now?
The old, this is the
You
old,
never told it
right?
right off.
Yeah, how do you
It literally says it in the directions.
Hey, someone
How do you
was
spell
Right there, list it as off.
I equals V over R, right? That remains the same, so don't worry about it. We're making a ratio
No, don't say
of
my
the
bad.
old one.
Oh, you went to the ratio of the.
You should know it, this is budget. I'm not saying
That's
budget.
bad.
You said it's not off.
What the?
Okay, there's cluster number 9.
Oh, okay, yeah. So it is bright.
Thank you.
Dude,
No, I swear, on my mom's life, that on my
Your mom should have
died.
died. Put that on trial, though.
And our mom's dead now.
Just let it go.
What'd you say?
Wrap it up.
We're good? Okay.
11
Yeah,
last
I'll
question.
figure it out.
Huh?
I'll figure it out.
Made a ratio. I made a ratio. I don't have to do it that way. I did the ratio with current.
What?
Did you
He's
do
gonna
11? That's the last
fun.
question.
Look at my work.
That makes sense, right?
Okay.
Right,
Yeah,
why?
that does.
I don't think 11 works.
What?
We
Wait,
somehow
yeah.
got it, didn't you?
We got like one off one.
No,
So-
no,
I didn't actually really do the math. I
One was
mean,
off. The middle one was off, right?
well, yeah.
Yes,
4
I
times
think so,
9.
yeah.
And then you just divide them.
So you might want
I'm
to
pretty
do
sure
that.
it's the path of least resistance.
Yeah.
No, Big Mike.
Why leave it there?
Yeah, the middle one.
Hey, you
Everyone's
just
trying to be
get
active.
points.
Okay, because basically
P
the
new
flows this way.
Yeah, everyone's trying to.
This is working. I got a question.
Gavin? You
What's
might
a
want-
That's actually smart.
So
So
say
say
again
again
a
a
second.
Trying to make fun of me, and then we're doing this.
Oh, actually,
We're literally doing this right okay.
they
Bro,
clash.
in the direction, it said to right.
Yeah. My bad.
Clash Rock Land.
16 over 9.
My bad.
Bro, we should play,
There. Is that good enough
I
for you?
wanna buy the thing where it's like.
Yep.
I mean, you
on a
should
track
probably
or something like
put
that,
P1.
Wherever you're trying to
69
guess what
P1.
skill it is. I wanna do that.
Why? I just did this.
You know what I'm talking
16
about? Yeah.
point. 69 times greater.
You know what, I'm just
Yeah,
gonna.
I've hit like
Yeah.
69
Called
so
Teams
P1.
inside
But I mean,
Well, this is what makes sense to me, and I wrote it out.
Yeah.
you know what? It's
I don't know, I mean,
Oh.
yeah, it's just the way that I did it.
Okay. Does that answer that question?
So does the current from the right, it doesn't choose the path of least resistance to be down, or most resistance would be down, so it's keep
Yeah,
going
so
left.
if you didn't have this side,
Uh-huh,
it would be coming up like this,
yeah.
right? If that side wasn't there, that side would be coming down like this. So basically, it's a logger jam here in the middle. So that's why this one doesn't have any brightness
They
to
don't
it.
just give it
But it's still basically completing the overall circuit, and that's why these two lights are on.
a.
So instead of going up, it goes to the right?
Yeah.
Very cool.
So basically, it's just one
Tab,
big
just click.
loop around it.
So is it the electrons just ignore the middle one then?
I thought it was just
Because it can't, because it's like, you're trying to force that current in
No,
the
there's
opposite
no,
direction.
instead of going
What
down.
happened if like one battery was like had like more
I thought it
volts
was-
than the other?
No.
Then you could have that possibility, but there
Well,
would
they
be
would
a pretty big difference.
Wouldn't there be a lot of resistance?
He's drawing it
It
as
would
if
not.
one of them was gone.
Well,
Will like the wire explode?
okay. Is that part, are we good with all of that?
Boom.
So make sure beside every one of those clusters, I see the predicted ones written clearly so I can read the numbers, and then the actual one. And if there's a difference, that's cool, you learned something from it, okay? I don't expect you to have every one of those right. And then staple that derived answer to that last question on the back. Mara?
Mike.